It's been a really long, scorching summer, and you're standing in front of a dispenser, filling your bottle with ice cold water. To your frustration, the dispenser works very slowly. You're getting thirstier by the second. Agitated, you grab your bottle and begin swinging it up and down beneath the dispenser nozzle as it fills. But are you actually making it fill faster? To answer this question, let's analyze how the rate at which water flows into your bottle is affected by the distance between the dispenser nozzle and the mouth of your bottle. But first, let us make some simplifying assumptions. For starters, as soon as any water passes through the mouth of your bottle, we'll call it done. So we're not considering the water level inside your bottle when making distance calculations between your bottle and the dispenser nozzle. Second, we are also assuming that water flows out of the dispenser at a constant rate, so there are no funny issues like the button not working, the water tank being close to empty, and so forth. Now, back to our question. Intuitively, you might answer that no, you're not making your bottle fill up faster, because moving your bottle up and down does nothing to change the speed at which water is coming out of the dispenser, and you'd be right. Except for one nuance. Okay, now let's try to tackle the problem the harder way. We first choose a height for our dispenser nozzle. Let's say it's 1 meter off the ground. Now, define f of t to be the distance between the dispenser nozzle and the mouth of your bottle at time t. But remember, since your cup can't get below the ground, there's an upper bound for the value of f of t, which is 1 meter. And there's also a lower bound of 0 meter because otherwise you'll be lifting your bottle above the nozzle. Other than that, you're free to choose any function you like, so long as its range is between 0 and 1 inclusive. Now, let's work out how long it will take any given drop of water to fall from the nozzle into your bottle algebraically. You probably already know from elementary school that to compute the amount of time taken for any kind of travel, you must divide the total distance traveled by the speed of the moving object. However, this is difficult to do when the drop of water in question is not traveling at a constant speed. To solve this problem, we are going to find a constant that can stand in for the speed of our drop of water and give us the same result. And you guessed it, that number is the average speed. So, what is the average speed of a falling drop of water? Well, ignoring air resistance, you might know that any falling object on Earth experiences an acceleration due to gravity of approximately 9.8 meters per second squared, meaning that the acceleration for a drop of water as a function of time is the constant function a of t equals 9.8. Notice how I'm assigning the positive sign to the downward direction since all falling objects travel only downwards anyway. Now, if we compute its antiderivative, we get its velocity function, v of t is equal to 9.8 times t. Notice how I am not adding an arbitrary constant of integration since we know that the water's initial velocity is 0. But what we really want is its average velocity, which, if you have taken an integral calculus class, you will know that this is the definite integral from starting time t to final time t sub f of v of s ds. And by the way, don't worry, s here is just a dummy variable, all divided by t sub f minus t. In our case, that final time t sub f is precisely the starting time t plus the time it takes for our drop of water to reach your bottle. Let's call this time taken little t sub big T. Also, note that our average velocity expression at this point is actually dependent on t, meaning that different drops of water have different average velocities depending on when they started moving. Great, so now we have all the information we need to compute the time taken by the drop of water to reach your bottle. But unfortunately, if your bottle is moving, then things are not that simple. You see, even as that drop of water is falling towards your bottle is moving, and so it is changing the distance that drop of water must travel. If your bottle happens to be moving upwards, that distance gets shorter, but if it's moving downwards, then that distance gets longer. So, we need to also work out the average speed at which your bottle is moving and incorporate this information into our formula for calculating the amount of time required. Notice, whenever the bottle is moving upwards, it is, in a sense, helping the water reach it. And so we need to add up their average speeds and then use that as the divisor of our distance function f of t to get the time taken. Speaking in terms of velocity, this is the case when the bottle's velocity is negative because the bottle is moving upwards. But when your bottle is moving downwards, the water has to chase it down to reach it. So we subtract the bottle speed from the water speed to calculate the time taken. So now our formula becomes time taken, this little t with a big T subscript, equals f of t, our distance function, divided by the difference between the water's average velocity, 4.9 little t sub big T squared, minus the initial displacement of 0 over little t sub big T and your bottle's average velocity, which is f of t plus little t sub big T, which is our distance function evaluated at the final time, minus f of t at the starting time, all divided by the difference between the final time and the starting time, which works out to be just the time taken little t sub big T. Then, doing some algebraic simplifications, we arrive at the following formula. Little t sub big T is equal to the square root of f evaluated at the final time divided by 4.9. As an exercise, you can verify this formula is correct by checking what happens when f of t is a constant function, meaning your bottle doesn't move. Okay, now that we have a precise handle on exactly how much time each drop of water dispensed at time t will spend to reach your bottle, how can we use this new information to find out how quickly your bottle will fill? To tackle this second question, let's aim our magnifying glass at what a rate really is. We can get a feel for this by first thinking about the discrete case. Say a drop of water comes out of the nozzle every second. Let's first look at the case for a stationary bottle. As you can see, the drops of water are reaching the unmoving bottle at regular intervals, meaning the bottle is filling up at a constant rate, which is also equal to the average rate at which it is filling up. But since your bottle is moving, each drop takes a different amount of time to reach it, so that the drops do not hit your bottle at regular intervals. Note that they also start their journey to your bottle at different times, giving the slanted alignment of starting points on the left. Then, the rate at which your bottle fills, or in other words, the rate at which the volume of water in your bottle increases, is inversely proportional to the average amount of time between drops when they hit your bottle, from the first drop all the way to the last drop that makes your bottle full. So, with this in mind, let us now zoom in on the differences between the arrival times of consecutive drops of water. As expected, these time intervals are shorter whenever your bottle is moving up and longer whenever your bottle is moving down. But what about the average rate at which the drops reach your bottle? Is it the same as the stationary bottle case? Try and explore that idea for a moment. Now, let's move on to the continuous case. Instead of dealing with individual drops of water, we will now consider a continuous flow of water from the dispenser to your bottle. Once again, we'll use a diagram to visualize the situation, but this time, the starting times at which water leaves the dispenser varies continuously, so I will represent this fact using a diagonal line on the left. Also, instead of numbering drops of water, the vertical axis now represents the milliliters of water that have already been dispensed. Next, just as before, we will represent the amount of time each little bit of water spends falling into your bottle using a horizontal translation of its starting point on the left. The result is a new curve plotting all the arrival times of water to the right of the starting line. Notice that this new curve is not a straight line parallel to the starting line because every point on that line has been horizontally translated by a different number of units to the right, a number given by little t sub big T, which is not a constant function of time. Finally, all that's left is for us to compare this right curve to what it would have been if you had not moved your bottle. In the stationary bottle case, all the points on the starting line are shifted to the right by the same number of units, since little t sub big T is constant. This means that the right-hand curve will just be a straight line parallel to the original. So, what's the conclusion? Well, graphically, it's obvious that it's only the last bit of water to be dispensed that makes a difference to the total time you have to wait at the dispenser. Which means that the next time you're really thirsty and need a full glass of water ASAP, just remember to only lift your glass closer to the dispenser when it is almost full.